something doesn't happen if you don't start the stream before the hour.
How do I not hack it, but I can't move it.
Something doesn't happen if we don't start before the hour.
Extra placards?
Extra what?
The placards, the time things, you set the 2?
I don't think so.
Okay, thanks.
I really hate to do this.
Evan.
We're having some technical
Evan.
difficulties. Could
Who
you
back one wrong?
Your hat is too awesome.
Well, it's, yeah,
It's giving me seizures.
yeah, your hat's gonna fuck the bit rate.
Oh, yeah. Is it still effective?
Just don't increase the
We
flash.
can't capture the slides, so we had to zoom out.
There's like my little vaudeville thing where if he doesn't stop, I can just throw him off face.
Is the rest of the crew still passed out from last night?
How long did you have to
Adam
drive
is
to get
out,
here?
right?
How long do you have to drive to get here? Oh, fuck. I was gonna complain about my 4 hours. See, I was hoping you would say, oh, I live here, and then I would say, really? Man, I had to drive 4 hours, that sucked.
That's it.
But no, you had to go and ruin at what you're being 10 hours away from your bachelor.
Whenever you're ready.
All right, so we're going to get started. I guess I'm just going to leave the door open, but that's fine. All right, so the title of this talk, I can be Apple, and so can you. If you're using Hacker Tracker, it says I can be Company X, because apparently they had to censor Apple out of the title. I just found out about this. So anyway, yeah, welcome to DerbyCon. Welcome to high noon, track 2. Thank you for coming. A little bit about my background. I was in the Marines back last century. I got out in this century, so it's right on the cusp. I was stationed in Hawaii and I worked in SIGINT. And the reason I'm in InfoSec today is because I got hurt in training. And I got put behind a desk for a year, and they told me to become a security officer for computers. And this is back when it was Windows 3.1, and basically there was no such thing as security. So I was like, okay.
There's no such thing as security for me as well.
Well, that's, you'll see that. That's my goal. So after the Marines, I went to the University of Florida. I worked for PwC, and then Booz Allen, Leviathan Security Group, and now I'm with Okta. Who here has heard of Okta? Raise your hands. A couple years ago, there would be no hands, so that's great. We're publicly traded now, so we've come a long way. No longer startup. And I'm on the internal offensive team. We like to offend people. Through our bug reports. So I work on the vendor side of the house, so anything that comes in that needs to be looked at for any potential hiding bugs, I will do that, and also look at infrastructure I look at everything from routers to web apps. So I'm a full stack pen tester. A real stack, not just the dev stack. Yeah, so I also write code for fun. That's my GitHub. I wrote Backdoor Factory, and I presented the first one 4 years ago, or at least the current version 4 years ago here at DerbyCon, and I introduced PDF Proxy. 2 weeks after PDF, 2 weeks after that presentation, I found this thing called Onion Duke, which was this was 4 years ago now. That was downloading, infecting binaries over Tor during download over HTTP. So that's enough about me. This is the outline. I'm kind of doing something different. I'm going in reverse. I'm going to show a demo, and then we're going to talk about how I found this bug. But I also have an update I added because some news came out 2 days ago that I don't agree with in the Mac security space. I'm going to talk about that. So what is code signing? Code signing is a security construct that allows for the consumer and user to verify who signed code in question and to verify that code in question has not been modified. Any failure in code signing, either at the OS level or in third-party developed tools, can have disastrous side effects, especially if you're in the defense side of the house or doing incident response. Okay? And both Windows and Mac OS support the concept of code signing for portable code. There have been issues in Windows code signing in the past. However, we're focusing just on the Mac side of the house today. So to talk about impact in code signing, we're not talking about lull bins or living off the land binaries per se. While it's a valid way to get code execution, a lot of the focus is on Windows. I challenge you to find lull bins in Chrome OS or iOS. They might exist, who knows? But I don't think so. But Mac OS does have a particularly interesting lull bin, which is Python. It's signed, it's protected by SIP, and so you can't look at the memory unless you have the entitlements or a kernel driver. But anyway, what we want to do is persist between reboots and fool the user that what we're running is safe and valid. And that's where code signing bypasses come in. As far as impact, code signing really impacts zero trust networks. If anybody know what zero trust networks are, raise your hand. Beyond Corp. So zero trust networks is the concept of you no longer have physical boundaries they're no longer a physical network, like a moat, for example, and you can have a device anywhere in the world, and we can make sure that it's secure and that we trust it just because your device is trusted and you have a token or something that says we trust you. Now, part of that is if you have a code signing bypass, then the whole entire security model for zero trust networks is broken. So you've got to have code sign enforcement, and you also have to have monitoring, which is a very important part. So I'm going to do a demo. This is going to show Google Santa, which is a whitelisting tool in full lockdown mode, and only Apple or native code can run Apple sign code or native code from the App Store. And this is going to show the concept of after a phishing attack or social engineering or some kind of post-exploitation where the user, or not the attacker, drops something to disk to persist between reboots. And this is going to show that you can have persistence and you can hide in plain sight. So let me pull that demo up. For those of you in the back, I hope you can't see this. I'm kidding, there's plenty of room. All right, on the left we have the user, the victim. We have a root shell and a regular shell. The root shell is on top. And then on the right we have the attacker terminal. So what I'm going to do here is show you, I'm going to run the calculator app. This is not the exploit. Okay, this is just to show that the calculator is just executing. Yeah, woo, y'all clap. Yeah. Exploitation's that easy. It just works. Too soon. So yeah, this is just to show that native app binaries are running. And I'm going to show next, I should be showing, this is Santa, the control. I'm just going to show what the status is, and it's in lockdown mode so that only Apple sign code can run. So I'm going to try to execute ncat or netcat, and of course it is blocked, as it should be, because it's not signed at all. Now I'm going to show where ls lives, and this is a maliciously patched ls with a backdoor in it, and it's in user local bin. And this is kind of neat because this is showing what the default. Who here uses Homebrew? Yeah, Homebrew. So if you do the default install, you have a privilege escalation bug if someone gets on your workstation. If you do anything, I'm going to show you that. And so I just dropped a malicious ls in user local bin. Okay? And so if I use ls, I get code execution and it contacts the attacker on the right. Okay? So now I'm going to show the path of root. And you see that user local bin is first. That's default. Okay, so if you have any root scripts that run through sudo, whatever, those, and you don't set the path specifically in the environment variables or in the beginning of the script, then whatever's in user local bin is going to execute. So just keep that in mind. So now I'm going to execute ls. And now I have a root shell. Okay? I'm not popping any counts for you, sorry. So next I'm going to turn off Santa, or put it in monitor mode. And I'm going to use Patrick Wardle's What's Your Sign tool to show that, to check to see if this is signed by Apple, or see who's signed by, and it says signed by Apple. And then I'm going to use CodeSign tool, which comes with the operating system, which shows code signing attributes. I'm going to show, you see com.apple.ls, that is an identifier that this is signed by Apple. And then I'm going to check to see if it's valid, and it says it's valid. Okay, and that's the demo, first demo. So, how does this work? Well, this was released June 12th, all right, and this made a pretty big splash. But the details are, so this takes advantage of the FAT universal binary format. What needs to happen is the first file in the universal file or FAT file, and I'm going to explain that in a second, must be signed by Apple and must be either i386, 64-bit, or even PowerPC. The malicious binary or non-Apple supply code has to be ad hoc signed and also compiled to i386 code if you're targeting, let's say, a x64-bit operating system. And you'll see why in a second. And the CPU type in the FAT header of the Apple binary must be set to an invalid type for the first file, or it needs to be a non-native chipset. And I'll explain this. So it exists in the difference between how the Mako loader loads sign code versus how improperly used CodeSign APIs check sign code is exploited via the malformed universal FAT binary. And let me fix my presentation. Okay, so this is the FAT file format. All right. You have two architectures, and each slice is the same program compiled for different target CPUs. So the i386 is for i386, and the x64 is for x64. Pretty simple. And there's no signing on the FAT file itself, so you can modify this all you want, just not the Mako binaries. And the vulnerability exists in the difference between how the Mako loader loads sign code versus how improperly used CodeSign APIs check the sign code. So let's create a Frankenstein binary. And how I did this, I compiled netcat to i386, and I ad hoc signed it, and I used the lipo command, which is a real command to create fat files. I kid you not. It comes with developer tools. You can use lipo to add, to create fat, or you can use lipo to thin it. I did not, this is not something I wrote. This is Apple back in the days when it was created. I don't know. So anyway, so we have our universal file or fat file. You'll see that Python is first, ad hoc signed or self-signed netcat is next, or incat is next. And I'll go over, so anyway, so I'm showing the cosign here, or at least the code signing here. So you'll see that netcat, it is indeed ad hoc signed, and the team identifier is not set. So this is important because you could abuse this. I'm just showing you Apple signed binaries, but you could abuse this on applications not by Apple if you could set the team identifier, and that is a challenge. There are no tools that do it right now. I would have to write one. So yeah. So we're just going to attack Apple binaries. So if I take and copy netcat Frankenstein to temp Python and execute Python, I get Python. But I want incat or netcat to execute. So how do I do this and not mess up the code signature? Well, what I do is I need to set the CPU type there in the box to an invalid type or a non-native type. By setting the CPU to an invalid type or a non-native type, the Mako loader will just skip over the signed Mako binary and execute the malicious code. That's how simple it is. So you take, here you see that Python is now executing incat. I get it to listen verbosely on port 8080, and it indeed is. You'll see that it shows that it is com.apple.python, and that it is valid on disk. So let's talk about who was affected. And everyone that I was able to test, that every third-party developer that I was able to test that use code signing APIs in their chipset or in their feature set, everyone that I was able to touch. Some people I couldn't get a sample of code before this came out, so I'm sure that there were silent fixes. So for each bug report, I provided 4 samples for the vendors to verify their bug and also to fix it. And each of these should return non-valid. Basically, the first one is, as it says, it's a bash binary. It's not signed and it has a malformed header. The next is a PPC binary. The malicious code is ad hoc signed and there's no malformed header. I found the PPC binary in a install disk for OS X Leopard that I had hanging around. I just pulled it off of there and then made this potentially malicious binary. And then, so bash ad hoc is just ad hoc signed binary with a malformed header. That means it's invalid CPU type. And then I created a terminal app. It's full application bundle. It is ad hoc signed and there is a malformed header. Terminal is kind of iffy when you go across different OS X architecture or versions. So little flocker, who's heard of little flocker? Yeah, if you have it and you haven't upgraded to Xfence, which also had it, you're still vulnerable to this. So Objective-C, so this is Patrick Wardle's tools. All his tools that did code signing checks were affected. I only signed one CVE because I like the work he does. I didn't want to punish him. So the first tool was what's your sign? Sorry. It's what's your sign, and then the next tool was I think Task Explorer. The green lock means that it was signed by Apple. So Google Santa, you'll see that it says whitelisted, and it's also everything's Apple. OS X Collector, the signing information. So OS X Collector only returned errors on invalid signatures. So I had to patch it up just to show that zeros meaning it's valid. Carbon Black, I don't know if anybody's heard of Carbon Black, but they came back as being signed by Apple. Virus Total, anybody hear of Virus Total? I hear they're decent. But yeah, and then OS Query, anybody know about this thing? Little Snitch. So Little Snitch had the best response. They would come back and say, hey, this is different than what's on disk. This might be maliciously modified, like in memory or something. But if you go and check and try to get more detail, it showed that bottom right, signed by Apple. And then if all your other tools are saying, hey, this is signed by Apple, it's fine, bro. And then you probably just let it connect out. A lot of people would. So people were like, what about Gatekeeper? Well, so this Gatekeeper wasn't affected if you use the application bundle. But also, let me just talk about Gatekeeper. And this is where I'm going to talk about some research that was released 2 days ago that I don't agree with. Gatekeeper is a security feature that enforces code signing and verifies the download applications before allowing them to run, right, one time. And that's off of Wikipedia, so it's true. So this is how Apple sees Gatekeeper. It's very awesome. This is how I see Gatekeeper. So if you've tested against Apple products, you know that Gatekeeper really isn't a security control. And we're going to go over that in a second. Gatekeeper basically keeps people that don't know they have a foot and a gun to keep themselves from shooting themselves in the foot with that gun. That's all it is. And it does help people that are not computer savvy to go and download an application bundle off of a shady website, that's not signed by Apple or by a valid developer certificate. So yeah, it does help people, but if you're pen testing against it, it's really not that good. So Patrick Wardle talked about this in his Gatekeeper Exposed talk back in, I don't know what year this was, I don't know, like 2016 or something like that. I'm going to go over the details here. So what does, on the left is protect, on the right will bypass, Gatekeeper. So in application bundles and DMGs downloaded over the browser. And also Apple can change these at any time. They can do whatever they want. It's their OS. So if you use standalone Mako binaries, that's why Homebrew executes when you download it. There's no Gatekeeper check at all. So that's what I use mostly if I get access to a machine. I just run Mako. So if it'll protect against zip bundles that you download over the browser, unless you use 7-zip. So if you use 7-zip, you can bypass Gatekeeper. If a tarred app bundle via the browser, Gatekeeper will check for that, or unless the user uses curl or wget on any of those file formats, and then Gatekeeper doesn't check. And also if you use it, if you're fishing via USB sticks and you're using an app bundle, there's no check, but I wouldn't use, can somebody get that door please? Thank you. I wouldn't use app bundles in general if you're pen testing. It's just not worth it. So this is where I'm going to make a detour. And I got nothing against the researcher that had this article come out, but it ended up in Wired. And if you're going to publish something in Wired, you better bring it. So this came out 2 days ago. It was a talk that happened at Virus Bulletin. And I don't really agree with concepts, and I'm going to tell you why. And here we go. So there are 3 main points. macOS does not check code signatures after first run. File infection is new. Applications should do self-checks to ensure no modification. Those are the 3 main points, and we're going to go over each one. So checking code signatures after first run, and my response is so what? And this is only for application bundles. Right? See my prior slides. And no other OS does this, right? There's no code signature checks on Windows on a default install. So this is kind of a non-issue. And if you do code signing checks, it has to be a binary load time where you're just being blasé about it, and that's really not a security control. So you're going to have a race condition. And if you do it at binary load time, we call it this thing called whitelisting. It's been around for a long time. And you can actually put your Mac in iOS mode right now with this command. And only Apple signed code can run from the App Store. It's very painful if you do that. I've done it. It's like, oh my God, I can't do anything. So if you do that, and the reason that this wasn't a suggestion is because it negates the need for AV, and they're at a Virus Bulletin conference, and he works for a antivirus vendor. So this is, yeah. Anyway, file infection is new. So file infection goes back to the 80s, right? And so it's not new. For Mach-O, in 2006, Roy G. Bitt, which I'm sure is his real name, introduced a page zero method, which is no longer usable because of changes in the file format. So 2006, 2012, OSX Reverser, or FG, introduced a library infection method. And then myself introduced a pretext infection method, and it's been in the backdoor factory since 2014. So it's definitely not new. And so the next point was applications should do self-checks to ensure no modification. Just show of hands, who thinks that's a really good idea? Who thinks that's a bad idea? Show of hands. Anybody? For those of you that are on the fence or have no hands, it's generally not a good idea. And you're going to have race conditions. Unless it's coming from the kernel, unless it's in the kernel, at boot, you're going to have race conditions. And if I can modify the binary, I can just modify the checks. So this is part of the article. As a result of this research, Reed himself added code signature verification to Malwarebytes Mac products, so they now perform a check every time they launch. And this is my response. So my second demo. So this, I got back after hanging out with Steve, my friend from high school that used to play drums together in marching band. How you doing, Steve? We were drinking last night, and so I get back to my hotel room at like 1:30 in the morning. I'm like, well, how long will it take me to bypass this? And it didn't take long. 10 minutes. I'm just going to show you this and put this to rest. All right, so on the right, same concept, got the attacker. I mean, on the left, got the attacker. On the right, we got the victim. And we got the recent version of the Malwarebytes trial. And so, let me start over. So what I'm going to do here is I'm going to copy this thing called settings test into the settings daemon. And it is a backdoor factory patched version of itself. It is not signed. When the backdoor factory runs, it removes the code signature. Okay. And then I'm going to kill the daemon, and then go to settings, and then you'll see that I get a shell as root. And then you'll see that, there's a self-check. Okay? So now I'm going to copy the normal one back, kill the process, and then I'm going to run backdoor factory. Thanks.
You're thirsty.
Do I have to do this now?
You can do it.
Oh, I really appreciate it. It's just Smirnoff Ice. I hear those are good, and it's really warm. I hear those are delicious. Anyway, so I'm going to execute backdoor factory here. And so what I'm patching here is their real-time protection process. I'm patching the process that ensures that it doesn't get patched. So I'm going to copy that over to the workstation, and I'm just going to run a real script that just does what I just showed you, just does it quickly. And then you see I get a root shell, right? I'm root. I am root. And you'll see that I didn't get any warning this time because I ran there's a race condition. So I'm just going to leave that there. And so I got nothing against the researcher, it's just I don't like bad ideas. And there's plenty of bad ideas in our industry as it is. We need more good ideas. So that ends the detour. So I decided to contact Apple about this bug. And on February 22nd, I sent the initial sample that was not self-signed to Apple. And I knew I would get this response. They said I need to do strict checking. So then I provided them a sample that bypassed their recommendation. And then they gave me another recommendation that didn't solve the issue. And then I told them how I hoped they would address the issue. And then they said that all third-party developers have to do this on their own. And they will update the documentation. So is Apple vulnerable? Now, I haven't found any real security boundaries in their code that would say, yes, they're vulnerable. Though, if you look at the System Information app, you'll see that this is my terminal app, POC, and it says that it's signed by Apple. Now, I hope you're not making security decisions from the Security Information app, but, so, yeah, just whatever. I guess it's not a bug. So, developer reactions were very good. This is one reaction, very succinct. This was another. And yes, God help you. And this is another, it was good. I'm going to let that go again because I love it. So, April 9th, I contacted all third-party developers that I could find. I contacted CERT and Carnegie Mellon, and they recommended a blog post because we don't know who is using these code signing APIs internally. I'm sure people are writing their own stuff, especially in the government. And on June 12th, we had the public disclosure. And so this is their documentation for the following API at the top, before, and then after. And so this paragraph specifically, I'm just going to call out a sentence or two. Be aware that the slices of the universal binary don't have to be signed by the same signer or the test to pass. One slice might be ad hoc signed, for example. Yeah, great. Yeah, that's it. So how do we, that was all, basically all that was updated. There was another API that was updated, but they do the same thing. One returns with errors, one doesn't. So how do we do this correctly? Well, there's different ways. If you're a non-developer or if you're working from the command line, you use CodeSign, and you have to specifically call Anchor Apple on the app or the PID. It can check in memory. Or if you're doing Apple generic, means anything that is from a developer code certificate that is rooted in Apple. Or you can use LiPo, that fun little tool again, to thin out the FAT file. Literally, it says thin. Pull out the 64-bit part, like out of login, for example, and then you can check to make sure that they're actually the same program, because you can mix and match different programs together. So for developers, it's really simple. You just call this set requirement create with string, and then you pass Anchor Apple or Anchor Apple generic, and then you call those flags there, all of them, and then you have to, depending on what you want to see, like OS Query, they have to break out each slice in the FAT file to ensure that they're by the same signer. And by increasing the complexity there, there won't be any more bugs, I'm sure. So penetration tester, if you are testing a product either internally as part of a product development cycle, or if you're testing against anything that does code signing, we have some samples there, Okta Security Labs on GitHub. And you can just download the samples and test against the actual product. And all those samples should come back as invalid. So how did I find this? Well, I've been doing code signing stuff for a while, just from the nature of writing EDF or the backward factory or file infectors. So this was an interesting bug, just outside of resources. And I gave a talk in 2016 about hiding from the investigator, and I found a kind of a weird bug. If I added padding to, the padding between each Mako is straight zeros. If you add anything in there, code sign would error out. It just says something happened. Sorry. So this made me want to look at the universal file format in a little bit more detail. I knew that there were more bugs, in that area. So fast forward with urgency, about almost 2 years later, I decided to look at this again. And for instance, I put a backdoor in Perl, and then I uploaded the virus total, and it was in a FAT file, and I got that it was signed by Apple. I was like, holy crap. So I knew I was kind of going on the right track here. So I come around February 13th, I'm really in a hurry to work on this. What actually happened is I had a kid, and I just, right after that, and I couldn't work on anything else. So, so one thing I wanted to see if I could create a malformed, a lipo, like a fat file with 2 chipsets of the same type. And I was like, can I do this? And I couldn't. You'll see that, as the error, it says they have the same architectures. Generally, if you have that kind of error, if something's trying to hamstring you from doing something to protect you, you want to do that thing. You just want to do that. What I'm like, okay, I'm going to do that. So I manually did it. I created a fat file that would do this, and then the Mako loader failed. I was like, okay. Then the next question was, how can I make this execute anyway? I want it to execute anyway. Can I mix and match? And that's when I found that if I changed the CPU types, I would get code execution. And after being able to create a malformed fat file, I was quickly able to make a fat file that would bypass the third-party developer code signing checks by using the Apple sign code first with an invalid CPU type. And everything else you've seen from the earlier parts of this talk. So, in conclusion, I encourage people to take a look at code signing, especially anywhere you see it, by any product. It's a core security construct based in math, and it's extremely complex. I believe that more third-party developers will make the same mistakes again, especially since the documentation is not very good. So, any questions? Yes?
Hi. First of all, awesome stuff.
Thank you.
Just 2 quick points.
Yep.
One, I was the speaker that spoke right after that research on VB
Yes.
2 days ago, and I actually said the exact same thing that you said. And he said, "Oh yeah, you're right, but then journalists are journalists." So the guy is aware. So
Okay.
Just wanted to say.
Okay, I just.
Record straight. Journalists.
Yeah, we went back and forth on Twitter, and he really enforced it. So he's digging in. But thank you. Thank you.
Second thing, you just helped me realize that thing about the fat binary. The only thing I didn't check when I released it, really long malware research. And I'm speaking about it tomorrow, so I just added your point to my slides and gave you some credit. So thank you so much for really helping.
You're welcome. Thank you. Any other questions? Yes.
So in your example, you have 2 code segments for different CPU architecture, and you try to understand. Can you add a 3rd or a 4th or a 5th?
Yeah. So I don't know if there's a limit, and if somebody wants to script that, it would be fun. That would be really fun. Like put 300 chipset architecture together with invalid types and see what the loader does. Maybe get code execution on 256. Who knows? I don't know. Any other questions? Yes?
You mentioned earlier that there's kind of 2 key aspects of it. First, code signing, please do it. And the second is monitoring. Speak more to the second.
So if you're, that was for zero trust networks. That was like if you're going to have zero trust networks, you need device trust. That means you have to have 100% accuracy that there's no malware on that device that could get session cookies out of the browser. So you need to have at least some kind of code signing on that device, right? Does that make sense? Yeah, and then you also got to have monitoring. So I mean, if you were to look at what's the most secure devices out there right now? It's Chrome OS and iOS, right? Because they enforce code signing all the time, unless you put the Chrome OS in developer mode. But then if you look at the monitoring on iOS and Chrome OS devices, it's not very good. So it's kind of a yin and yang, shoot, pick your poison kind of thing. Any questions? Any other questions?
Yes.
Yes.
Yeah. I'm not 100% sure, but wouldn't iOS use something like ARM Trust Zone or something like that to ensure that everything is signed?
iOS right now does code signing. Right now, it's its bread and butter.
I mean, does it do it through hardware, like a lot of
It's through the kernel.
Okay.
I mean, I think everything. I mean, I'm not an iOS expert, or at least hardware expert. I know there's a secure enclave that ties everything back. Any other questions? All right. Thank you very much.